Un, deux. Hop. Okay. All right. Good morning. Okay. So today will be the 8th lecture for the course. So just to give you a summary of where we are currently in the course. So we have been talking for a few weeks about uncertainty and then probabilistic modeling for 2 lectures, and then about machine learning for 2 lectures as well. So what we'll start doing today is to merge everything together. So we'll be using the few things we have learned together about probabilistic modeling to take decisions. And so we'll be combining basically probabilistic models with reasoning over time and also with search problems. So this is what we'll be doing today. And we'll do that in a mathematical framework, which we call Markov decision processes. Okay? For today, we'll assume that everything is known. Okay? So all the components of these environments are known. And then we'll try to see how we can come up with algorithms to design optimal agents. And then next week, we'll relax this assumption and we'll say that actually the environments are unknown and we'll have to learn about them to be optimal. Okay? So that will be the topic of the last lecture for next week about reinforcement learning. Okay, so what we want to do today is to reason under uncertainty. That's something now we know how to do, but the thing we'll now do on top of that is to take decisions, okay? And then we'll have to define what we mean by decisions and more specifically what we mean by optimal decisions, okay? So to answer this, I will formulate the problem or the setting as what we call a Markov decision process, an MDP. And then in this framework, we'll see the Bellman equation, which will tell us how to recover the optimal policy, the optimal agent. And then we'll see a few algorithms, value iteration, policy iteration, modified policy iteration, to obtain this optimal policy. Okay? So in the first part, I will just assume that the environment is fully observable. Okay? We have a complete access to the state. And then in the second part of the lecture today, we will consider then what would happen if the environment is only partially observable, and that will lead us to something that we call partially observable Markov decision processes, or POMDPs. Okay? Okay, so to set the scene, we'll assume a very, very simple setting today, which is the case of a grid world, in which we have a 3x4 grid. We have an agent inside, and the agent can move freely from one cell to another. Okay? So you know the location of the agent somewhere on the grid. It can take up to 4 actions. It can decide to go forward, to go right, or to go left. Okay? The twist is that the outcome of this action is not known exactly. It will be stochastic. So what will happen is that with 80% chance, if you decide to go forward, then that you will arrive to the state that the agents wanted to go. But it could also happen with 10% chance that you arrive either to the left or to the right position. Okay? So instead of moving forward, you arrive to one of these 2 orthogonal positions, and that may happen with 10% chance. Okay? So this is in contrast with what would happen with deterministic action, when if you say you move forward, then you know that you will arrive to this cell above with 100% certainty. Okay? Now we are dealing with uncertainty, so we'll have this kind of uncertainty to account. Okay? What is also new is that the agent will receive rewards at each time step. And so we may have different kind of rewards. We may have small rewards that we obtain at every step because the agent lives. Okay? So it can get either positive reward if it's still living, but it can also obtain negative reward if, for example, we want to reach some position, some terminal state as quickly as possible. Okay? We may also have big rewards that we obtain because we encounter states that are specials, like, for example, terminal states. So, for example, here we could reach this state and get at once a big +1 reward. But we could also obtain big negative rewards, like in this case, if the agent falls in this hole, then it gets a negative reward and actually dies. And that would be modeled by just saying that this state or this one are terminal states. And so after reaching these states, no more actions can be taken. Okay? And then in this grid world, the goal will be to design a policy to maximize the sum of rewards. Okay? So you want basically to maximize the score of the game. Okay? Now the question that we'll be trying to answer today is how do we find a policy, so a function which gives us the best action to perform at every state of the game, at every state of the grid. Okay, so to answer this problem, as I said, I will first formalize it in terms of what we call Markov decision processes. So it's just a name to say that we have an environment which we define by 4 elements. So we say that a Markov decision process is a tuple made of these 4 elements. We have first a set of states. Then we have, so in the case of the grid world, it could be all the states that you can reach. So all possible positions for the agent. Then we have a set of actions, which could be dependent on the state, but to simplify, we just say that we have a set of actions. Then we have a transition model P, which we'll define as a conditional probability distribution over the next state, given some starting state, and given some action A, which is performed in state S. Okay? And we'll assume that this transition model is stationary, so it will not change with time. Okay? You can assume it remains the same, that the physics in the sense of the game or the environment remains the same at every time step. And finally, and that's the new component, we have a reward function, R, which will map rewards to states. Okay, so that's a function that you can evaluate at any state S, and which will give you a small reward as just a scalar value, okay, between -infinity and +infinity. Okay? We'll assume that these rewards are not stochastic, so when you reach some state S, you always obtain the same reward. Okay? There are variations of Markov decision processes where the reward themselves could be stochastic, but we'll not consider that. Okay, now the setting, and I will draw this again because I will have to reuse it, is this loop in which we have the agent, okay, or robot. Then the agents will be taking actions. Taking actions. These actions will have an effect on the environment. And the result will be that the agent will reach a new state S prime, which we assume to follow the transition model. So S prime is a random realizations from the transition model, given that we perform the action A in some state S, which is known to the agent. Okay? And together with the state, we can also evaluate the reward function. Okay, so we'll know the reward value in the current state S. Okay? And basically, what we want to then what we want to do when we say that we want to solve a Markov decision process is to find a policy pi, which will be a function which takes some state S, okay, and produce some action A, okay, which will give us the action that we should perform. Okay? So this will be a policy. Okay, so to give you an example of all these components, so for the grid world, the set of state S, so this one, would be all the possible locations, let's say ij of the agent on the grid. Okay, so in this case, we would have 11 of them, one for each of the cell. Okay, and I'm saying 11 because in this case, we have this cell which we cannot reach. It's a wall. Okay, so we can't traverse this one, and the agent will never be able to reach it. Then the set of actions would be up, down, right, or left. The transition model would be this conditional probability distribution, which encodes this stochastic distribution. Okay. And finally, the reward could be, let's say that if the state S is a non-terminal state, then the agent obtain a negative reward of, let's say, minus 0.3. On the other hand, if it reaches one of the two terminal states, either this one or this one, then it will get a reward, which could be either +1 if it reaches the diamond, or -1 if it falls in the hole. Okay? Okay, why do we say that Markov decision processes are Markovian? This is just due to the assumptions that we are making about the transition model. Okay, we are saying that given the present state S, the future and the past are independent. Okay, so we could have said instead that the conditional distribution of the next state, S prime or ST plus 1, is dependent on ST and the action, but also could depend on the previous states before ST, so ST minus 1, and the action that was used to reach ST from ST minus 1, and so on and so forth. And you could incorporate, if you wanted, all the previous states up to the initial states and the very first action. Okay? So we are making independence assumptions by saying that given the present state, so given ST, the future, ST plus 1, and the past, so ST minus 1, ST minus 2, and so on until S0, are independent. And because of this assumption, we can rewrite this conditional as just this simpler conditional of ST plus 1 given ST and AT only. Okay? So basically, we are making a similar assumption as in search problems, where we are defining instead, if you remember, a function result taking S as input and the action as input as well, and would give us S prime, the next state, as output. Okay? And this is a similar assumption because here we are not including states before S to determine the next state S prime. Okay? All right. So what do we want to solve? In an MDP, we want usually to find an optimal policy. So a policy is some function pi, which is a mapping between the set of states and the set of actions. So given a state, produce an action. Okay? And we want specifically the unoptimal policy. So a policy which would give us, in expectation at least, the largest sum of rewards. Okay? So a policy, as I said, is a mapping between states, from states to actions. An optimal policy is one that maximizes the expected utility. So in this case, the expected sum of rewards. Okay? Which means that in a sense, if we know this policy, then the agent that will be running this policy is nothing else than a reflex agent, as we saw in the very, very first lecture. Okay? This is also slightly different from expecting minimax, if you remember this algorithm, because expecting minimax did not compute entire policies, but only some actions for a single state. Okay? Here we really care about finding this function, so for every state, all optimal actions. Okay? And not just for one state specifically, the optimal action. Okay? So you see there an example of a policy, and specifically of an optimal policy when the leaving reward is minus 0.3. Then the optimal actions are given by the arrows. Okay? So if you are there in the bottom left corner, the optimal action is to go up, not to go right. If you are there in the top left corner, the optimal action is to go right. If you are there, the optimal action is to go up, and so on and so forth. Okay? What you should already realize before trying to answer, but how do we actually find this optimal policy, is that the optimal policy is, of course, dependent on the rewards that you obtain in every state. Okay? If we define the optimal policy as the policy which would maximize the expected sum of rewards, then of course, if depending on the value of the rewards, the optimal policy will change. Okay? So here you see on the left the optimal policy if the leaving reward was minus 0.004. So you see that it's different from the previous one, and it's different specifically for this cell, where instead of going up, like here, the optimal action is to go to the left. Why would that be the case? So it seems that intuitively what the agent should do is to try to reach the +1 cell, because it will get a very big reward if it reaches it. Okay, and then the game will be over. So why then is the optimal action for this cell to go left? Okay, which means it will take longer to reach this cell than if it was going up directly. Yes?
Because you won't take the risk to go to the 2, 4, to the -1.
2, 3. Yeah, so this one. Exactly. So because the outcome of the actions is unknown, okay, it's stochastic, what could happen is that if you go up, okay, so if you are in this state and you decide to go up, the outcome could be that either you reach this state or this one, okay, because of the 2 random outcomes that could also happen with 10% chance. And in particular, if we are there, then what could happen next is that when it decides to go up, certainly, then it could happen that it actually reaches and that it reaches the state and then dies and then gets a big negative reward. So there is a risk if you pass through this path in order to reach this +1 reward that actually you will never reach it because the actions will fail and you will actually die and get this negative reward. Okay? So there is a trade-off between living and the cost of living and taking the risk of reaching maybe faster these bigger rewards. Okay? And this is exactly what happens as you see in these 4-order plots, depending on the value of the living rewards. Let's start with this one, which corresponds to the previous scenario. So when the living reward is between -0.4 and -0.08, then the optimal policy is given by this. And here you see that for this cell, the optimal action is to go up directly, okay? Because actually going through this other path is in a sense, costing too much because of the longer path it would take and the higher or the greater sum of rewards you then would have obtained instead of maybe indeed taking this risk, but at the end, the path, if you manage to reach it, would be smaller. Okay, so when you compute the two expected sum of rewards, the optimal action would be to go up directly. It's also interesting to see what would happen when you get, for example, very big negative rewards, let's say below minus 1.6, then the optimal action is to die as quickly as possible. Okay, because if the agent lives it for every time step that it lives, it will pay a cost of minus 0.6 or greater than that. Okay, and so the optimal action then is to reach as quickly as possible a terminal state, even if this terminal state is a state in which you reach this negative reward. If you have a very small negative reward but close to zero, closer to zero than before, like if it's between minus 0.02 and 0, then you see that the behavior is still a behavior that will lead to reaching the diamond, but it will do so using a behavior which is very cautious. So instead, for example, for example, this one is interesting. Instead of going up and then taking the risk of reaching the minus 1 cell, the optimal action is to try to go to the left. And so with 80% chance, this is the actions that would be reached, but then you would not reach this state in gray. Instead, you would stay put at the same position. But with 10% chance, if you decide to go left, then you could reach one of the two perpendicular positions. And by deciding to go left, you could actually go up or down. Okay? But never, ever, you will go right and reach the minus 1 reward. Okay? So in a sense, this is very inefficient, but that's the price that you're willing to pay because the price of living, in this case, is very small. Okay? And when the living reward is actually positive, then the optimal policy is to never, ever reach one of the two terminal states. You just stay put, and then you just keep collecting the reward that you get at every time step. Okay? Okay, so what you should realize is that these rewards that you get, they will really they will have a strong effect on the behavior of the optimal agent. Okay? And depending on the value of the rewards, you will see a balance between an agent which would be taking risk and an agent which on the other hand would be very cautious. Okay? Which would be very conservative. So that means, by the way, when maybe you will have to design yourself an MDP, because you want to model an environment in a setting, you will have also to decide on these rewards, and they will have a very strong effect on the optimal agents that then you would obtain. Okay? And that's a very difficult problem, how to design rewards that leads to actually what you want. But for now, we'll just assume that these rewards, they are given. Okay? We know this reward function. We are not trying to modeling a reward function. We just assume it's a given, and then we'll try to then extract the optimal policy from there. Or unoptimal policy. Okay. What's also a bit different from before is that now we have rewards or utilities over time. Okay? We are collecting these rewards over a sequence of several time steps. Okay? And then we have a question to answer which is what preferences should an agent have over states or reward sequences? Okay? Should the goal of the agent to collect the largest sum of rewards or the smallest sum of rewards? And if, like in this case, we have reward sequences, so each one of these sequence is a sequence of rewards. So this is a notation, for example, to say that at the first time step you get a reward of 2, at the second time step a reward of 3, and then at the next time step a reward of 4. Okay? So should you maximize or minimize the sum of rewards? And also, if you have two sequences of rewards for which the sum is the same, should you prefer this one, in which you prefer to obtain the rewards soon or now, as quickly as possible, or are you fine with waiting for a bit and only collecting the rewards a bit later at future time steps? Okay? So this is something we have to decide. We have to decide what are the preferences. So in our case, we'll maximize the sum of rewards, okay? But we'll decide on when we want to collect them by a trick which we call discounting. I will talk about that in a moment. But basically, what is important is that we'll assume that we have what we call stationary preferences over reward sequences. So what does that mean to have stationary preferences? It means that if you have two reward sequences for which we are saying that the agent prefers this one over this one, and we say that using this symbol, okay, to prefer, but the structure of the sequence is such that the first reward is the same for the two sequences and then different, then if we say that we have stationary preferences, then it implies that necessarily we will also prefer then the reward sequence of the suffix of the first over the reward sequence of the suffix of the second. Okay? And so if we say that, okay, we are coherent in this way, we have these stationary preferences, then actually there are only two ways to assign utility values to reward sequences. The first one is what we call additive utility. Okay, it's just to say that the utility V, and this is a notation I will use over and over. So V will denote the utility of a reward sequence. The utility of a reward sequence, in the case of additive utility, is simply the sum of the rewards. Okay, nothing special about it. Or, and that's the way that's what we'll do today in the lecture, we could also assign utility value to reward sequences by using discounted utility values, in which we have a sum of rewards as before, but we will discount by a factor gamma the rewards that we obtain at every time step. Okay? So that means that for the first reward R0, we'll not have any discounting factor. Then we'll have gamma times R1 for the reward for the second time step, then gamma squared for the third time step, and so on and so forth. Okay? So in this case, we'll use a geometric series to characterize the utility of a reward sequence. Okay? And this discounting factor will be a value between 0 and 1. Okay? So why are we actually doing that? Or what happened exactly when we say that we are discounting? Well, when we discount, basically we are saying implicitly that we'll prefer less rewards that we collect into the future. Okay? And we'll prefer them less by a factor which will be proportional to, or exactly by a factor of gamma to the power of the number of time steps between now and that state that we reach. Okay? So that means that each time we transition to the next states, we'll multiply in the discount once to compute the, or to specify the actual rewards that we want. Okay? So why do we discount? As I said, because we'll be preferring sooner rewards than later rewards. Okay? That will also be helpful later on when we want to define an optimal policy. If we have a gamma factor or discount factor which is too close to 1 then usually that will lead to policies that will be more difficult to obtain. Okay? All right, so as an example, here you see the utility value that we would compute for a discount factor gamma of, let's say, 0.5. Then the utility value of this sequence 1, then 2, then 3 would be plus 1, then plus 2 times the discount factor, plus 3 times the discount factor squared. Okay, and so the sum would be equal to 2.75. Okay? And implicitly, that also means that in this case, we would prefer, if we have these two sequences of rewards 1, then 2, then 3, or 3, then 2, then 1, they have the same sum, 6. But if we have this now discounted utility, we would be preferring this second sequence of rewards over this one. And the reason being that in this case, we would be collecting the big rewards sooner than in this one. Okay? So basically, it just means that if gamma is smaller than 1, then the agents will be greedy, okay, and will try to collect the bigger rewards first. Okay? But the closer gamma or rather, the closer gamma to 0, the more greedy is the agent, and vice versa. The closer gamma to 1, the less greedy is the agent. Okay? Okay, so now we have defined utility values for sequences of rewards. Okay, but we still have an issue is how will we characterize the utility values that we assign to sequences that maybe could be infinite. Okay, we could have several sequences of states that are infinite that do not lead, if we stop time, to the same sum of rewards, but if we consider what would happen to infinity, then both would sum to infinity. Okay, but really are these two sequences of similar value? Okay, so we have an issue comparing rewards sequences with plus infinity utility will be problematic. So we have to fix that. So there are several solutions. The first one is to assume that we have a finite horizon. So we only compute the v values, the utility values, up to some horizon t. Okay. Or similarly, we could assume that we terminate episodes after a fixed number of time steps, big T. That's usually not something we'll do because that will mean that now the policy will no longer be stationary. It will depend on the number of time steps which is left. So that will be, that's something that you can do, but we'll not consider that in this lecture. What we'll consider is something like this. We'll consider that we are discounting. Okay, we have a discount factor gamma which is strictly smaller than 1. And also we'll assume that the maximum reward that we can obtain for every state is bounded to some maximum value, which we'll call R max. Okay? In this case, then the utility value that we would assign to any sequence, and even to an infinite sequence of rewards, then by definition would be equal to this sum, this infinite sum, so this series of discounted rewards that we obtain at every time step RT. But if RT is bounded above by some constant, then we can compute analytically a bound on this geometric series, which in this case is given by R max, the maximum value, over 1 minus gamma. Okay? So that means now even if we have infinite sequences of rewards, using this trick, we'll not have infinite values for the v values. Okay? These values will be bounded. Another trick that we could also use is to assume that we have an absorbing state. So that means no matter what the agent do, there will always eventually what will always eventually happen is that it will reach a state which is terminal. Okay? It will not be able to stay put in the same state for infinitely many time steps. Okay? But if we are doing this, then we are making assumptions about the environment, which can be reasonable, but the simplest really is just assume that we are discounting the rewards and that we have bounded rewards. Okay, so now assume that we have a policy, pi. Okay, so it's a mapping between a state and some action. Okay. So let's say that we are currently in some state S. Then the agent runs the policy. The policy tells the agent it should perform some action A, which is given by the policy pi. Okay. Now, since the environment is stochastic, it's the same as if the agent was reaching one of these chance nodes, if you remember. Okay, in which case the chance node here would be associated to the starting state and the action decided by the policy. Okay, so we are there. Okay, we have chosen this pair S and A, but then we don't know the next state that we will reach. Okay, so we could reach some state here, or maybe this one. We don't know. But we'll get to one of them, S prime, okay, with some probability value, which is given by P of S prime given S and A. Okay? Which means that if you start in some state S and run the policy, okay, which is deterministic, the policy is deterministic. The policy always gives you one action and not a random action. But the trajectories that you will visit, they will be random. Okay? Why will they be random? Because the transition model is random. Okay, so that means for every execution or infinite execution of the policy, we'll obtain a trajectory of states and rewards. We'll get so if you only keep the rewards, we'll get a trajectories or a sequence of rewards. Okay? But this sequence is a random object. Okay? Do you all follow that? If we start again the same game in the same state, we run the same policy, we may reach a different set of states because of the random transitions in the transition model. And the resulting sequence of rewards might be different from the first one that we obtain. Okay? Which means that the quality in this case of the second sequence of rewards might be different, or the utility or the value of this second reward might be different from the first. Okay? And we can repeat that many times, and we now have to deal with the distribution of sequence of rewards. Okay? And so then we have an issue, which is to define the utility that we assign to a policy, pi, which is fixed. And what I will say is that the utility of some policy pi when you start in state S, okay, is the sum of expected rewards that you obtain, is the sum of, it's the sum of discounted rewards that you obtain. So the rewards. So these are the rewards that you obtain along the sequence of states from 0 to infinity. These rewards, they are discounted by gamma, okay, to the power of t. Okay, but this value is random. Okay, because it depends on these random objects, which are the states. Okay, so what I need is then if I want to fully characterize the quality of the policy, what I can do is to try to evaluate the expected value of this discounted sum of rewards. Okay? Okay? Where now this expectation is over the random sequence of rewards that we would obtain by running the policy pi when the state, the initial state S0 is S. Okay? So this is what we call policy evaluation. So it gives us, given a policy and a starting state, a value, okay, a number. And this number is defined as the expected discounted sum of rewards, okay, that you obtain when you follow the policy pi starting in state S. Okay, so now we can characterize a policy. We can give a number to a policy, which is the only thing we need then to define what we mean exactly by an optimal policy. An optimal policy would be a policy for which this value is the largest. Okay, so among possible policies, all possible functions that are defined as mapping from state to actions will say that the optimal policy is the policy pi star, which will maximize the expected utility, so for which v pi of S will be the largest. Okay? Now, there is, you see that these optimal policies for now are defined as function of the starting state, okay? But actually, because of the discounted utilities, the optimal policy, and that's something we'll show in a few slides, is actually independent of the starting state S. Okay? So the optimal policy so the policy for which this is the largest for some starting state S, and the other policy for which this would be the largest for some other starting state S prime, well, these two optimal policies actually are the same. Okay? And so because of that, I will drop the S in the notations, and I will simply denote pi star as the optimal policy. Questions so far? Yeah.
Is it unique?
No. Yeah.
Can you review for is it independent?
But that's something we'll cover in a few slides. Okay. So we have defined the value of a policy as v pi of S. Okay. From there, we have defined the optimal policy pi star. And now what I will do is to define the values of states. So I will define as Vs the value of a state as simply the value that you could obtain if you were to follow the optimal policy starting from S. Okay? If you were optimal, what would be in expectation the sum of expected rewards that you would obtain starting from S? Okay? So this quantity is quite interesting, and it should be contrasted with the immediate reward Rs. So Rs is the value that we obtain immediately when we reach a state S, and on the other hand, Vs is the long-term reward or sum of rewards that we could obtain starting from S. Okay? Okay, so here in this grid, you see the utility of states, so the VS values. So for the optimal policy, I'm not telling you yet how to obtain this optimal policy, but just assume that we have it. Then if we compute the V value for each state, you would get all these numerical values that you see there in the grid. Okay? So you see, for example, that for this cell in the last row, third column, the V value is 0.0611. Okay? And that would be the case when the discount factor in this case is equal to 1 and the leaving reward is equal to minus 0.04. Okay? Now, what can we do with that? Can you, from these numbers, extract the optimal policy? So you know that the V values are computed from the optimal policy by definition. But if I show you only this grid, can you extract out the optimal policy? So this mapping from state to action. So how do you use this number then to determine an action? Yeah.
So for all states, you just choose the action which gives you the maximum expected reward.
So what we want is to define pi, which is a function of s. We assume that we know Vs for any s. Then what do you say?
You choose the maximum R of S prime in all of the actions that you can make, in the rewards, the expected reward of all options that you can make.
And so do you mean something like the expected reward?
Well,
This?
no, not the short-term one, the long-term. The ones that we computed.
V?
Yes.
Okay. And what is S prime?
All of the actions that you can make.
Or the next state that you could reach potentially by picking A?
Yes. Accounting for the stochasticity.
Okay, so, and how do you account for the stochasticity?
P of S prime knowing S and
And then you sum. Exactly, that's exactly what you should do. If you know these numbers, then you can extract the optimal policy from them by saying that what you will be doing is to pick the action for which the expected values of the next state is the largest. Okay, because that's what you want. You want to maximize the expected sum of rewards in expectation. And here we are explicitly accounting for these uncertainties, okay, by using the transition model. And this would give us then the long-term reward that we would obtain starting from S prime. Okay? And you see here that there is no immediate reward Rs because we are already in S. So we have already collected the reward, and this reward that we've collected will not have any effect on how we, or should not have any effect on how we pick the next action. All right, so this is called policy extraction. So using the principle of maximum expected utility, the optimal action maximizes the expected utility of the next states, okay? Meaning that, exactly as you have said, the optimal policy pi star is the one that will maximize the expected values of the next state S prime. Okay, so that gives us a way to maybe obtain this optimal policy. Okay, if we say we want to build an optimal agent, what I'm saying is that if we know this v value, because of this, if we know the v values, we can just plug them here in this equation, and we will have obtained pi star. Wait a minute, but Vs itself depends on pi star. So how could I know the v values from which I could extract the policy if the v values are themselves dependent on the optimal policy that I'm trying to obtain? Okay, so we'll answer that after the break. But basically, we are there at this step. If you want to be optimal, then first you take the correct action, okay, which you can do by just following this equation. And then you just have to remain optimal. Okay? And you have to remain optimal because you will be following the optimal policy in the next state S prime. Okay? And you know that if you are optimal, then the expected sum of discounted reward will correspond exactly to V. Okay? So that seems easy. You are optimal for the first step, and then you just continue for the next step. Okay? Okay, let's take 10-minute breaks. We'll resume at 10. Okay, so just to summarize, so we are dealing with an agent in a stochastic environment. The agent has to take some actions, but it does not know the outcome of these actions, and we'll model that with a stochastic transition model, which means that we'll assume that the next state S prime will follow a conditional distribution of the next state S prime, given the starting state in the action. At every time step, we'll collect rewards, okay, as a function of the state. What we want is to find a policy. A policy is just a mapping from a state to an action. And this policy will tell us what to do at every state. Then we have defined the utility or the value of a state for a policy pi as the expected value of the sum of the discounted rewards if we were to follow pi starting from state S0, or state S. Okay? Now, given this definition, we can give preferences over policies and say that specifically that the optimal policy is the policy pi star for which this quantity is the largest. Okay? Using then the definition of an optimal policy, we'll say that the utility of a state S is the utility that you could obtain if you knew the optimal policy and were following that optimal policy starting from state S. Okay? Then we have defined the optimal policy from V by saying that the optimal policy is the action. So the optimal action starting in state S is the action leading to the largest V value in expectation over the next state S prime. Okay? But then we noticed a circular definition. If we say that the optimal policy is defined in this way, as function of V, but if we define V itself as a function of pi star, then we have a loop in our dependencies, and It seems that we cannot go forward. Well, there is a trick, fortunately, which is to think for 2 seconds about exactly what is the V value of a state. What is the utility of a state? Well, the utility of a state, when you reach it, it's equal to the immediate utility that you get when you reach that state S, plus the sum of rewards that you will get next. Okay? And if we are discounting, that means we'll be discounting the remaining utility values. Okay? And if we are following the optimal policy, okay, the utility value that we'll obtain will be this quantity exactly, but discounted by a factor gamma. And this equation is really, really, really important. This is what we call the Bellman equation. And this is the only thing that we need to find the optimal policy. Why is that? Well, actually, this Bellman equation is not one equation. It's a set of equations, one for every possible S. Okay? So basically, you can view that as a system of equations in which you have unknowns. These unknowns are the V values that, if we knew them, we could derive the optimal policy from. Okay? But if we have this, then that means we have as many equations as we have state S. So we have a system of equations, as many as we have states, okay, and we have as many unknowns. So we can just solve the system for V. That's it. Now, if you manage to solve the system of equations, you will have recovered V without knowing pi star. But if you know V, then you can extract out pi star. All right? So this is called the Bellman equation. As I said, these equations they form a system of n, so where n is the size of the state space, or the set of states of equations with as many unknowns. But what is a bit difficult about this system of equations is that these equations, they are nonlinear. Why are they nonlinear?
Because P can be anything.
This is just a value. It's a coefficient. It's a number.
But it's
Yeah, but we don't have to solve for this. Okay? You can evaluate P for any S prime, any S, any A. So there is nothing unknown there.
Because each subsequent step depends on the previous one, and so it's every equation will depend on the previous one.
So what? So if I had written something like this, V0, V1, V2 equals to R0, R1, R2 plus gamma of so we have, let's say, 3 states. We would have a sum, in this case, of P0, that's some coefficient that we associate, let's say, to state 0 that maybe we could reach, okay, times V of 0 plus V1, V1 plus V2, V2, right? This would be different now. Okay, we have something like this. And all these values there, they are known. Okay, we can just read them from the transition model. Okay, so we have three equations with three unknowns, the V1, V0, V1, V2. Yeah.
That's the max, which...
Yeah, sorry, there is also... It should be a max. So the issue is that we have this max here. And this is where the nonlinearity comes from. So you have one example here. By the definition of the Bellman equation, for example, the value of the cell 1, 1 is the immediate reward that we get, minus 0.04 plus gamma times the maximum among four different choices, because we have four different actions. Okay, and for each, we would arrive somewhere in one of the states, and for each of those states, we would obtain some value, okay, which are defined in this case by the v values. Okay, and the issue is that we have this max over these four choices, okay, which makes the equation nonlinear. Can you solve nonlinear equations or systems of nonlinear equations?
Depends on the equation.
Could you solve this system of equations?
With a machine, maybe. With my hand, no.
Okay, and what would you do with this machine?
Numerical.
Okay, you would put numbers and then exactly what, so if you have access to a computer, how do you solve this system? Yeah.
Could use some sort of dynamic programming algorithm.
Yeah.
So compute, I don't see it from here, but like some value which you can compute directly, from it compute others. I'm sure you can actually do that.
Yes.
Just to iterate.
Okay. And what would you do at each step?
V1, 1 equals some initial value,
Uh-huh.
and then wait until it converges.
Yeah, but what do you do between the initial values and convergence?
But,
What?
you calculate the n+1 step.
The n+1 step, yeah.
There are two methods, but I don't know how to implement them very well in this case. But would be Newton-Raphson or some fixed point iteration?
Yeah, you could use a fixed point iteration. That's exactly what we do, what we'll do there. So if you solve this system using a fixed point method, you arrive to an algorithm which is called value iteration. And it's a mix of the ideas that you have said. So we'll maintain a vector of estimated state utilities, okay, and we'll update this vector across several iterations, and we'll name the vector that we have at iteration I as Vi of S. Okay, and this will be an estimate of the actual target utility that you want to obtain or estimate. Okay? And what we'll do at every step is to make this vector a bit more consistent with these equations. And the trick is just to say that the updated and now more consistent estimate of the utility values, so vi plus 1 given s, is just equal to the Bellman equation using the estimated utility. Okay, so we'll say that the updated value is the immediate reward plus the discounted value of the maximum expected v values. But in this case, these are not the v values. It's the maximum expected estimated v value. Okay, we are using here our estimate of the v values, our current estimates of the v values. Okay? And then you just repeat that until you converge. Okay, so we arrived to a very, very simple algorithm in which you initialize the, so in this snippet, it's not u, it's not v, it's u, but these are not the notation of the textbook, but in the literature it's usually v instead, but these are the same. So we initialize use to, yeah, this is the loop. So you initialize them to 0, and then you repeat this until you converge. Okay, and what do you do at each step? So you iterate over all the states in the set of states. Okay, then you say that the next iterate u prime of the v values for the state s is equal to the immediate reward plus the discounted maximum expected estimated utility for the same state. Okay? Not the same state, for the state S prime that you would reach from S. Okay? Then you also compute basically just the largest change between two states, two u values. Okay, so you just compute if this difference is large enough, so larger than some threshold, or larger than the bigger change that you had before. If it's the case, then the biggest change is now that difference, and then you repeat until you reach this quantity. Okay? So let me show you that in code. So here I've just re-implemented the grid world we've considered in the slides. Okay, we have two terminal states. These two, so the top right corner and the cell just below. I'm considering a leaving reward of minus 0.4, discount factor of 1, and I'm using this transition model. You reach the state with 80% chance, the one you wanted to go to, or you can go to one of the two perpendicular directions with a probability of 10%. Okay? Okay, then here you just have some code to implement the transition model. Then you get the leaving rewards, unless you are in a terminal state. Then you just have some other value. So minus 1, where is it? Terminal states. Here you would get either plus 1 or minus 1. Then you have value iteration, the algorithm. You initialize the v values just to random guess initially, or just to zeros. And so here you see that I will iterate over every state, every combinations of x and y positions, so ij pair. And I'm just checking if all these pairs correspond to valid states, because we have this wall in the middle. Then you have a big loop where you iterate. And at every step, you will be computing a new estimate v new. Okay, what do? Then you iterate over the states in v, the current v values. If it's a terminal state, then, okay, you can compute its v value exactly directly. It's just the immediate reward that you get in this terminal state. Okay, there is nothing after. There is no more action in the terminal state. So the v-value initially for this terminal state are just equal to the rewards. Otherwise, if it's not a terminal state, then you compute for each action the expected utility, estimated utility of the next state. Okay, so we iterate over the actions. And then for each possible action, then we iterate over the, so we compute some quantity that I will call Q. Then you iterate over the possible next state, okay, by being in the current state, taking this action. You may be in one of these three states, okay. Each will happen with the probability that we get from the transition model, okay, which we multiply with the v-value associated with this next state. Okay, then you sum, you get a Q value, which you compare to your current maximum Q value over the previous actions that you've already considered. Okay, and then you update your estimate of the v-value by saying that v new for that state is equal to the immediate reward plus the discount times the maximum Q value. Okay? Then you compute if now so you can compare the change of value from before and now, after and before the update. Okay, and you compare that to the biggest change. Okay. And then you repeat this loop until the biggest change is smaller than some threshold that you set. Okay, and then you just run value iteration again. Okay, and you see that, okay, sorry. We reach convergence after 20 iterations, and the v-values that we obtain are these ones, which should be, unless I've made errors, the same as these ones. Okay, so all these values are the same as these ones. Okay. And you can extract out the policy from the v-value. Okay, how do we do that? We iterate simply over the states. If the state is a terminal state, the policy is to do, the action that we should do is nothing. Otherwise, we just compute the action for which this quantity is the largest. Okay, so we just have a for loop over possible actions. We compute these Q values. We pick the one for which Q is the largest, and then we associate to the states the best action. And if we do this, then we'll have this mapping from states to actions. So in this case, I've encoded the actions in this way, but if you want to see what they are, then we would obtain these actions there that you see, which are the same as before. Okay? Questions? So you see that to obtain an optimal policy and optimal agents, basically the only thing we need is to implement this equation. And in 50 lines or so of Python, we are done. Okay, what about now the quality of this algorithm? And specifically, what about the convergence of this algorithm? Will we, sorry, yes?
I just wanted to ask, is there a way to estimate the discount?
It's something you fix. It's not something you estimate. It's a given.
But
So optimal is a function of the discount. Yes? Okay, so what about the properties of this algorithm? Will it always converge? Well, you can prove that, yes, that's the case. And so specifically, if you consider Vi and Vi plus 1 to be successive approximation of the true utility, then we have a theorem which says that for any two approximations, Vi and Vi prime, okay, when after making a Bellman update, okay, we'll have that the difference between the two updated approximations will be smaller than before. Okay, mathematically it means that the difference between Vi and Vi prime for any two initial approximations, okay, and we measure that in the sense of some norm, let's say the infinite norm, so the largest difference in this case. What we'll have is that this difference will be smaller after a Bellman update. So the difference between the updated Vi, so Vi plus 1, and the updated Vi prime, so Vi plus 1 prime, okay, will be smaller than the difference of the initial guess, and will be smaller by a factor of gamma. So at every iteration, we'll shrink the gap by a factor of gamma. And so this is quite powerful because it means, in particular, that if one of our guess, one of the two Vi or Vi prime are the actual V values, the one we want to estimate, then we know that we'll shrink the difference by a factor of gamma at every iteration or value iteration. Okay, because this is true for any two pairs of approximations. So one could be perfect, okay, and we'll know that we'll reduce the gap by a factor of gamma. Okay? And so what we say is that the Bellman update is a contraction by a factor of gamma on the space of utility vectors, okay, which means that any two approximations must get closer to each other. And what is interesting for us is that, in particular, any approximation must get closer to the true V value. Okay? And from this, we can show that value iteration always converges to a unique solution of the Bellman equations, and that will happen whenever gamma is smaller than 1. What about performance? How fast? So we know that we'll contract the estimates, but concretely, how many iterations do we need? So since we have this contraction, what this contraction also means is that the error will be reduced by a factor of at least gamma at every Bellman update, at every iteration of the algorithm. Okay? So it means if you say that you want to approximate the V value by doing a maximum error of, let's say, 0.1, okay, then you can just repeat these iterations until you know that the maximum error you would get should be necessarily below this threshold. Okay? So if you assume, for example, that the maximum initial error is bounded by twice the maximum reward over 1 minus gamma, okay, then, which is something that, so you could say that you know in advance what will be the maximum reward, okay, that's a reasonable assumption. Of course, you know the gamma factor, okay, so you know this quantity, okay, and so you could assume that, well, you initialize V0 such that this is true, okay, and then you just have to repeat Bellman update. You know that this largest error will be reduced at every step by at least a factor of gamma. Okay? So that means this quantity will shrink by a factor of gamma to the power of n, okay, where n is the number of iterations. So it will shrink exponentially fast with the number of iterations. Okay, and so that means with that you can, without actually knowing the true values, you can still determine the number of iterations you should do under these assumptions to reach a largest error of some threshold that you pick, let's say epsilon. Okay? And here you see that because of this, the performance of the algorithm now will depend on the discount. If we have a discount factor which is close to 0, okay, then this the denominator will be close to 1, okay, and you will need few iterations. On the other hand, to reduce the error. On the other hand, if gamma is close to 1, okay, we'll have 1 minus something which is almost 1, so that will be a number close to 0, and we'll at the denominator. So that means the initial error will be huge, okay, because you will divide by a number close to 0, so you will actually have a very large number, and therefore it will require more iterations to reduce the error. Also, you see that the gain that you get, if gamma is close to 1, then the gain that you get, the reduction that you get at every iteration is small. If gamma is, let's say, 0.99, then you will just reduce the error by 1%. If gamma is 0.1, then you will reduce the error by 90% at every step. Okay, so you have huge differences depending on the quality, on the performance of value iterations, depending on the value of gamma. And you have plots showing you that also. Okay, so yes?
Why not trying to find a discount factor below 0.5 if we see that's even better? Or is it just because you didn't show it on the slide? Or is that threshold?
No, of course, you could continue this plot to the right. But what is important is that, okay, you could set gamma to obtain the optimal policy fast, but the optimal policy would not be the same. So the optimal policy that you get there is not the same as the one you get there, because this one would be very greedy, and this one would consider the entire horizon to make its decisions. Okay, so it could be that actually the expected sum of rewards, or actually the sum of rewards that you would get for this optimal policy or this one are quite different. Okay, so this is a nice and short algorithm, and from which we can obtain the optimal policy. But there are several issues with this algorithm. The first one is the cost. So if you notice, at every iteration, we have a cost to pay which is proportional to the square of the size of the state space. Okay, because we have as many equations. And then for each equation, we may have this big sum, which could be also proportional to the size of the state space. Okay, so this is a very long equation for each state S prime, as long as the size of the state space. And also, because of the max, we have to iterate over every possible action. Okay, so the time complexity is at least quadratic with the size of the state space and linear with the size of the action space. Okay, so for a grid world like ours, it's fine. Okay, but for something like even Pac-Man, the one that you had to deal with the project, the size of the state space is much larger. If you think and try to enumerate all possible states of Pac-Man and the ghost and the dots and whatever, it's huge. Even for small grids, it's huge. Now you take this huge number, you take the square of that, and then you multiply this again with the number of actions. So that can be, and that's the price you have to pay at every iteration. Okay? So then if you multiply this with a gamma factor which is close to 1, then you would have to pay this price many, many, many times. Yes?
What if the environment is not discrete?
Yeah, that will not work. No, you can't do that. We'll see how to do that when we talk about reinforcement learning next week.
And same for if the actions are.
Yeah. So yeah, that's a very good point. Everything that we are talking about today is assuming a discrete state space and a discrete action space. If you have possibly infinitely many states because you describe them using continuous numbers, or if you have infinitely many actions because you define them also from continuous numbers, then this algorithm will not work because you see that we have you have this max, so that means you will have to iterate over infinitely many actions. I don't know how to do that. And at least if you implement that naively, and then here you would have to iterate over all possible next states, and you have infinitely many. So there are tricks, and you can approximate these quantities, but strictly speaking, this is just assuming discrete variables. Okay, the second issue beyond the cost is to notice that, okay, you may have a good enough estimate of the states, or you may have some utility of the states, but after the update, the Bellman update, okay, where you do this, it may be that the actions that would be chosen through the max remains the same. Okay, if you make a tiny change to vi to obtain vi plus 1, it's very likely that the optimal choice for the actions remains the same. Okay, so the max at each state may rarely change. And third is that the policy pi I that you can extract from the estimate vi, this policy actually may already be optimal even if the state estimates, the value estimates are inaccurate. Okay? Because the only thing that you need to extract the optimal policy is to correctly order the actions. You may be wrong about the exact values, but as long as you order the actions correctly, such that the first action should be the optimal action, that's all that matters. Okay? So we may actually have an optimal policy even if V is inaccurate. So that means when you run value iteration for thousands of iterations, let's say, it might be the case that we are running all these iterations for nothing if the only thing we care about is to extract the policy. Okay. Then from this, there is a variation of the algorithm, which we call policy iteration. And instead of directly computing the v-values and updating the v-values, what we'll be doing instead in this algorithm is to maintain an estimated policy, and we'll do updates on the policies directly, not on the v-values. Okay? So the policy iteration algorithm instead directly computes the policy instead of the state values, and we'll do so by alternating two steps. The first step is the policy evaluation step, which is basically to say that we'll be computing, so we have a guess, a current guess pi for the policy that we want to, for which we want to converge to the optimal policy. Let's call it pi or pi I. For this policy, we'll estimate the v-values. Okay, we'll evaluate the v-value. Okay, and then from these v-values, then we'll make an improvement to the policy directly, not to the v-values, by doing a one-step look ahead based on the current estimate. Okay, so we'll say that then the next iterate of the policy, pi I plus 1, is given by the action A, which maximizes the expected utility of the next states, where we estimate the utility of the next state from the v-values that we have extracted from the current policy. Okay? And we can show, I will not do that, but we can show that this algorithm is still optimal, but converge much faster under some conditions. Okay, so how do we evaluate the policy to implement step 1? Step 2 is trivial, you just code this equation. So how do you extract out vi from some policy pi I? Well, in this case, so instead of computing V for the optimal policy, if what you want is to evaluate the V value for some policy, which could be whatever, the V value for this policy is given by the immediate reward that we get because we've reached state S plus the discounted sum of next rewards. Okay? But here now, we are not following the optimal policy, so we don't have this max. We just pick the action which is given by the policy by I. Okay? So that means this max disappear, and we just have a sum over the next states, S prime, starting from state S. But now we are not iterating anymore over the action. We are just following the action given by pi I. Can you solve these equations? How? Yeah. Sure, that would work. Can you do something better? Are these equations still nonlinear with respect to V? They are just linear equations. Okay? Now we are back to a system of linear equations. You've had entire courses on this topic. So you can use a very efficient numerical algorithm to solve this system. Okay, so you can, so now we have a system of linear equations, okay, because we have removed the max. We have n equations, one for each state, okay, with as many unknowns. Okay, and this can be solved cubic with a type complexity which is cubic in the number of states, okay, using standard linear algebra methods. Okay, which is fine, but honestly, it is still too slow to my taste. If you have a large state space with, let's say, a few millions of them, which is not very big for any problem, then you would have to take the cube of that. That gives you the cost you have to pay at every iteration of policy iteration. Okay, so that's a big no. However, what is interesting to notice is that maybe it's fine if we don't find this solution exactly. As long as you just improve our estimate of V, that's all we need. Okay? So an approximate solution is usually sufficient. And one very simple trick is just to perform k iterations of simplified Bellman updates as before, but without the max and following at every time step pi. Okay? And this one, so we would have a cost now which is linear in S and linear in the number of iterations that we say we want to perform. Okay? So we would be just basically solving the system of linear equations using a fixed point method, but only very approximately by just running k iterations. Okay? And if you do that, then you get an hybrid algorithm which is called modified policy iteration. Okay, so you have something like this. And in terms of code, I can show you that this works. Okay, so again, you have a piece of code now to evaluate the policy. So you start from a grid and a policy, so a mapping from state to actions. And then you have this loop to evaluate the policy, which is where I do the modified policy iteration algorithm. So I estimate these v values, okay, very approximately, by running 20, in this case, 20 iterations here of Bellman updates. Okay, and I will use that as an estimate of the v values for the policy. And then, in policy iteration, you have again a big loop. First step, you evaluate the policy. Second step, you improve the policy by doing a one-step look ahead, where you say that so you iterate over all possible actions. For each, you compute the expected estimated utility of the next states. Then you just remember which one of those actions led to the largest estimated utility, and then you associate to the state for the next iterate of the policy the best action that you have identified. Okay, and then you can repeat that until you notice that the policy is stable. Okay, you don't update the actions any longer. Okay. Okay, and here you see that if I run this algorithm, in only 3 iterations of policy iteration, I obtain the same v value. Okay, but honestly, this is maybe a bit cheating because inside these 3 iterations, I'm also doing 20 iterations of Bellman updates. Questions on this? Nope. Yeah.
Can you use this technique on a not fully observable environment?
Yeah, we'll talk about this in just 3 slides. Thank you. Okay. Okay. This is an example of using MDP and value iteration or policy iteration to solve a game. So do you know about this game, 2048? So you can actually model this game as a Markov decision process where you have a set of states, S, which is just a set of all possible configurations of this 4x4 grid. It's large, but that's something you can do. Then you have 4 possible actions. You can either swipe left, right, up, or down. Then the results. So when you swipe, let's say, left, 2 numbers that are consecutive will merge and become the sum of these 2 numbers. But also, there is a tile which will appear somewhere randomly on the empty cells with a value of either 2 or 4. Okay? And then you get a reward, let's say of 1, if you reach the winning state, or a winning state, in which you have a cell where the value is equal to this target, 2000. And you may say, for example, that for any other states, you don't have any reward. Okay? So do you agree that if you can define this, you have just a regular Markov decision process? Okay. Therefore, you can use the algorithm that we have seen. And so this guy spent too many evenings writing these bugs. But so he formalized everything in terms of this Markov decision process. This is the kind of diagram or transition model you would get for just 2x2 grids. Okay. Then he defines the rewards, values, policies. You should recognize these equations now. The optimal policy. Okay, and then if you run policy iteration, for example, to obtain the optimal policy on this 2x2 grid, this is what would happen. Okay, and then it stops. If the goal in this case is to reach a value of 8. Okay, so you can just repeat that. It's become more difficult to scale to larger and larger grids, even if 3 by 3 is still small, but the size of the state space increases very quickly. So if you consider a 3 by 3 board with, where the goal is to reach 1,000, then there are 25 millions of states. So the size of S is 25 millions. That's huge. Oh, that's not too small. And then you can load the policy that you would identify if after running the algorithm, you'd get something like this. So who is good at this game? Yeah. So how would you define or try to explain the policy that you are implementing to your neighbor?
We say we need to try to put the maximum value near each other to don't lose cell as we don't want to have minimum value near a maximum one.
Okay. Okay. Yeah, that makes sense. But how do you go from this intuition to the next action you should take at every time step? You can do that. So this works for 3 by 3, and then you can also see what happens for 4 by 4 grids with the target of 2000. And by the way, even if it's optimal, it's not always successful. Okay? These are not synonyms. Okay? You may be playing optimally, accounting for all the uncertainties and all the randomness of the game, but it does not mean that you will always win. Okay? Because of bad luck, these random tiles which appear may be in very bad settings, which eventually would prevent you from solving the game. Okay? But in expectation, you are optimal. Questions on this? Nope. Okay, then I will quickly go over this part and then we'll have the break for the exercise session. Nope. Where is it? Up. Okay. So there was this question, can you apply this when the environment is only partially observable? The answer is no, you can't. Because if your environment is not observable, if you can't observe the states, then you don't know the states that you are in, and you can't evaluate this conditional distribution. Okay, because you don't know this one. And also, you don't know the reward. Because if you don't know the state that you are in, you cannot evaluate the reward. So can you still formalize the problem to be able to solve it? The answer is yes. And what we'll arrive to is the concept of a partially observable Markov decision process. Okay? So a POMDP is an MDP in which the state is not fully observable. So the agent does not know in which state S it is in, which means it cannot evaluate the reward. It cannot evaluate, it cannot evaluate the possible next states for the current state, since it does not know what is the current state. And also, it does not really make sense now to talk about a policy in the same way, because a policy is defined as a mapping from state to action. But if you don't know what is the current state, how can you evaluate the policy? What will happen instead in a POM-DP is that the agents will collect observations, percept, through a sensor model, so something that we can assume to follow a conditional distribution of possible observations given state S. Okay? From which then we can reason about to try to infer possible values of S given the observation E. Okay, so formally we'll assume that now, since the agent does not see S, but only partial observations of S, it must maintain some beliefs about what are the plausible state values. Okay? So we'll do that by saying that the agent maintains a belief state B, where B will represent a probability distribution over the states, and this probability distribution will encode the current agent's belief over its states. Okay? So it will not know for sure what is the current state, but will believe that maybe it is in this cell, or maybe it is in this other cell. Okay? And this belief will be encoded as probability values. Okay? That we put in a belief state, which I call B. Okay? So B is a big vector with as many entries as you have states, and each entry Bs simply denotes the probability value of being in that state S under the current belief. And then what will happen is that at every time step, we'll not see the current state S, but we'll get a new observation. We'll get an observation E, which we assume to follow to be a realization from the conditional distribution P of E given S. Okay? And that should remind you of what we have seen 3 weeks ago. This is exactly a filtering problem. We have a system which evolves through time. We don't know the state of the system. We just get partial observations of the system. And we have algorithm then to estimate the state of the system. Okay? So this is exactly like a filtering problem. So to summarize now, in a POM-DP, we are in this scenario. We have an agent. It does not know its current state S, but instead maintains a belief B about possible or plausible states. Then, as before, it must take actions A. These actions will have an effect. So effectively, the agents will transition to a new state, as before. It will transition to a state S prime under the same assumption that there is this, that we have this transition model P of S prime given S and A. But it will not see S prime. What it will see instead is a noisy observation E prime that we assume to follow from this conditional of P of E prime given S prime. Okay? And then this observation is passed to the agent who then updates its belief. Okay. So how do we then act under this setting? Well, fortunately, there is an important theorem from 60 years ago now already, which says that the optimal action depends only on the agent's current belief. Okay, you can only, of course, be optimal depending on what you know. That's just what it means. So that means the optimal policy can be described by using a mapping from what the agent believes to an action. And so the optimal policy then, mathematically, can just be described by a mapping, a policy pi, taking as input not a state, but a belief about the states. Okay? So the optimal policy can be described by a mapping from beliefs to actions. Okay? From a belief state to an action. Okay? And what is really important for you to understand is that the optimal action does not depend on the actual state S that the agent is in. It does not know about it anyway. It only depends on what it thinks about the plausible states. Because optimality will be relative to these to these beliefs. Okay. So what's the consequence of that? Is that a POM-DP can be reduced to an MDP. So you can go from a partially observable MDP to just the framework of a regular MDP, provided that we can define a transition model from a current belief state to a next belief state. Because in a regular MDP, so we are in this setting, the agent must know its states, then it will observe the next states. If you are in this setting, then we can evaluate. We have everything to define an MDP. Now, what I will say is that in a POM-DP, or we can go from a POM-DP to an MDP, if we just rename the states to B, okay, instead of knowing the actual state, we just have belief states. From this belief state, we'll take actions, and we would be back to an MDP if we could find a transition model from a current belief state to a next belief state. Okay? And then the next element we need is now a reward over the belief state instead of a reward over the states. Make sense? Now, the question is, okay, but how do you define this transition model over belief states? But do you agree with me that if we can define this transition model over belief states, and if we define a reward over belief states, we just have a regular MDP, which is not defined over states, but over another space which I call a space over belief states, but which are states of some kind. We have the actions, we have a transition model over B's instead of S, and we have now a reward over B's instead of S. So that's mathematically just an MDP. Okay? Now the question is, how do we define this guy? How do we define, and this is maybe a stretch, so B is a belief state. So it's a probability distribution over current states. And what I want to define is a probability distribution over next belief states, meaning over, so I want to define a probability distribution over probability distributions, because B's are probability distributions. Okay, and I want to define specifically a conditional probability distribution over the next probability distribution of the beliefs, given the current distribution of the beliefs, or the current distribution of the states that we believe in, and the action. Okay. So let's see how to do that. Okay, let's say that B is the current state, the belief state. Then the agent performs some action A and then perceives E. Okay? So we are there. The agent knows about B or believes in B, takes some action A, and then observe E prime. Can we determine B prime? Well, the answer is yes. So we don't know the current state, but we have a belief about it, which is BS. Okay? So we can just enumerate over all possible states. Okay? And for each of them, we have a belief. And then for each of them, on the other hand, we know the transition model. Okay? So we know that if we think we are in this state, then there is a probability of PS prime given S and A to reach that other state. Okay? So this quantity we can compute. And then if we believe then under this assumption of, okay, if I'm actually starting in S, then reaching S prime, and then observing E, then I can, so this is, by the way, just a push forward. Okay, you have a belief, you push it forward through your transition model. You get the updated belief at the next time step, and then you make an update by observing E, okay, to pre-weight the state S prime. Then you normalize, and you get your updated belief state B prime. Okay, so this is just filtering as before, nothing new. Now, how do we go from this? Oops, sorry. How do we go from this to a probability distribution over the belief states? Because that's the element that we need to go back to an MDP. So we need to define the transition from B to B prime when we take the action A. Okay, so this can be written by having a sum over the conditional joint of B prime and the and some observation E conditionally on B and A. Okay, this can be factorized by having first P of E given B and A, and then having P of B prime given B and A and E. Right? Then what about this one? So this is where we have to deal with the states. So E could be the result, is the result of some state S. Okay? We don't know about exactly which state, but we can reason about it. So P of E given, so that means we can just rewrite this again by considering the joint over E and S prime, and then marginalizing out the next state S prime. Okay? So we may think that we have reached S prime. So we have a belief P of S prime given B and A. Okay? And under this assumption, then the probability of some observation E is given by P of E given B and A and S prime. Right? Now, P of E given B and A and S prime can be simplified to just P of E given S prime. Okay, to this. And now we have to reason about, okay, what is the possible next state we have reached if we believe we are currently, if we have a belief B and then take some action A, then this is just a push forward of the belief state. We think that we are currently in S, we push it forward to the transition model, and that will give us the probability distribution over the next state. And now you see in this equation that we have all the terms that appear, we know them. B of S is just the current belief state. P of S prime given S and A is the transition model, okay, over the states. P of E given S prime is the observation model. We also assume it's known. And then we have this, P of B prime given B, A, and E. And then the trick here is just to say that this term will be equal to 1 if indeed B prime is the result of a forward update using a filtering algorithm from B, A, and E. Otherwise, it's equal to 0. So the answer is yes. We can define this transition model over belief states. Next ingredient, we need to define a reward now over belief states and not over states, but we can just say that we just will consider as a reward over belief state the expected reward that over the states that we think we are in. Okay, so we just have this sum over all possible states, and then we sum over the reward we would get for each state times the beliefs that we have to be in this state S. Okay, and now when we plug all these things, now we are in this scenario, which is exactly an MDP. Okay, so we can reduce partially observable MDPs to regular MDPs. And it seems then that we have solved our problem. Unfortunately, the answer is not as simple. Even though the reduction is correct, we don't have any algorithm now to solve this MDP. And the reason is that this MDP is continuous. This MDP over belief states is continuous because the belief states are continuous. Okay, so that does not really help. And specifically, if you take value iteration, policy iteration, modified policy iteration, none of them will work, okay, because they can't work with continuous variables, continuous states, continuous actions. And in fact, if some of you are interested, solving POMDPs efficiently, or just even accurately first, is still an open problem. So if you have good ideas, there is some research to be done on this topic. Which is unfortunate because most interesting problems where you have to take decisions will be problems in which, well, everything is not observed. So that means for most real-world problems, we don't have any, well, we don't have good or optimal algorithms. Okay, can we go around this problem? Well, yes, you can always make approximate solutions. And so very quickly, and then that will be the end of it for today, you can consider online agents, agents that would try to approximate the solutions and would try to do so only for the state it's currently in. And in these 3 slides, but I will just, I think, skip them. Basically, you can design an agent which combine a Bayesian network, or more specifically a dynamic Bayesian network, so a Bayesian network which is replicated through time at every time step, to which we add decision and utility nodes. Then you combine that with a filtering algorithm, and you do something similar to expected minimax under this setting, and you would obtain a decent algorithm to solve POMDPs. That I can skip. Questions? Okay, so let's take a 10-minute break, and then we'll resume with the exercise session. Thank you.